So welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Dr. Brian Ichter, who is a research scientist with Google DeepMind, and there he works in the robotics team. So something about Brian: before joining Google, he received a PhD in aeronautics and astronautics at Stanford, and his research is about enabling mobile robotic systems to plan, reason, and perform long horizon tasks in real-world environments through machine learning. And in particular, in his recent work, which is also what he's going to talk about today, he was focusing on the application of large-scale foundation models to robotics. Today, he's going to talk about limitations, properties, and applications of foundation models for robotics. This is clearly a hot topic, as we can see from the diverse audience today, and I'm very excited to hear more about it and give you the stage, Brian.
Awesome, thank you. And yeah, feel free to interrupt throughout. The presentations take over my whole screen, so I might not hear, but if you chime in, I'm happy to take questions as we sort of go. And yeah, as you said, I'm going to be talking about foundation models for robotics, and I thought maybe the first thing to do, we could start off with a quick demo of a real robot. So this is running in our lab right now, and Chad kind of set up this demo for us. I figured I'd make it somewhat Halloween related. So we have some candies that we want to hand out to people. And what's really nice about using foundation models is that you have language as this interface. So it's very kind of straightforward. They're very general. So I can say something like Chad likes peanut butter and his favorite color is blue. And we'll see, you can actually see the code that that it's writing will be in this bottom left if it updates. For some reason, it's not receiving it. So if it doesn't read it, then it might be that it. Okay, I got that. So it's a
demo effect.
Yeah. All right. So it says okay, great, and then it greeted me, said hi there. Let's have it hand out the candies and see so this requires a couple reasoning steps. First, it has to understand that peanut butter refers to the Reese's Pieces. It has to understand that when I say someone's favorite color is blue, that this is the bowl that he should put it in, and then has to connect it down to actions that the robot can actually accomplish. We can also do things like put the Skittles in the bottom right corner, and this is there's some frame of reference that it has to understand. It has to map these down to coordinates that it can actually execute it with. And again, yeah, you can see the code as it runs. It looks like it actually wrote the right code, but for some reason it didn't execute it. So we'll just say the same thing again. And yeah, we can also say put the other candies in. And this one, putting it in different corners is actually one of the first things that we tried when we were starting to play with language models. And we're kind of this is sort of a hard thing to express, different means anything other than what you've already done. For some reason only. And here, last candy, that's also somewhat hard to recognize what exactly that means, but it can do this naturally. Some of these have been, for some reason, it didn't write that code, but so on the fly, you can sort of interact with it. It's really nice that it's interpretable. Another thing that we can do is be somewhat metaphorical and abstract. So just say imagine the bowls are the biomes of the earth. This is something that Andy Zhang, who has done this demo several times, kind of came up with, and it's just a weird way of thinking about it, but it's really nice that you have these language models to process that, and it's something that algorithmically I think would be very difficult to write down. So show me what happens when ocean. So here it can connect the idea that ocean is blue and forest is green. So this is the way that I would accomplish this, and then turn that into an action and execute it. So I'll jump back to slides now, but afterwards we can also play with this some if people want. But yeah, so a lot of this talk is going to be about how we kind of get to this stage where things really work. And I think clearly the sort of elephant in the room is scale is foundation models, starting with transformer architectures that can ingest these like huge amounts of data, whether it's Wikipedia data, internet text data, coding, dialogue, or even vision now, videos now. So these foundation models obviously scale with size. They get better and better at a pretty wide range of performance, and sort of are at the point where, I mean, I think this chart is maybe a year old, where we were just hitting human average performance, and now in a lot of cases, we're actually exceeding human average performance, and even in limited cases, better than some of the best humans at very specific tasks. So yeah, the capabilities are kind of going nuts, starting with chats, but also generating images, understanding dynamics that you might need to know to be able to create a video, editing them, understanding how to weave images into text and answer questions about them, and even understanding audio. Each of these sort of is built on this backbone of foundation models that is extremely like powerful in general. There's also a fair amount of natural overlap with what we care about as roboticists. So the reasoning abilities of language models are really, I guess, impressive, and means that we can often map their thought process down onto a robot. The semantic knowledge that's in there is huge, and something that before we had a lot of trouble somewhat expressing. So, understanding that this is a banana and that a banana is a fruit, and that maybe the banana goes in the drawer, knowing what else is in the drawer, knowing to get something in the drawer, you first have to open it and then close it. Like all this types of semantic knowledge and reasoning is really useful and naturally in there. But there's also a lot of challenges. There's first grounding. So each robot is different. The state of the world matters. The state of the robot within that world matters. It is not something that they have a lot of data on. There's also a lot of interactive decision making. To get something out of the drawer, you need it to have opened it. You need to actually like affect the world, and that effect causes this feedback loop. The like unsupervised training of foundation models causes some problems. We see it with hallucinations, for example, where they haven't seen this sort of interaction with the world. They haven't tried something, made a mistake, and then had to back out because everything was just unsupervised relabeling. There's also, compared to like internet scale data, pretty low amounts of data in robotics, and the quality of it is extremely low. It's very difficult to get expert robotics data in general, let alone at the scale that we need or that's on the internet. We also often, I think now we're starting to see vision a lot more. We're starting to see a little bit of audio, but the sensing modalities that are predominant in robotics, also like depth, semantic segmentation, things like that have not been sort of like the first class citizens, I guess, of foundation models. So putting that in there makes a big difference, though I think vision is coming a long way. And then also safety matters a lot. Like you can't necessarily make a mistake. Also, I think I hear like some amount of echo. I'm not sure if it's a question or if it's just like my voice. But yeah, so I think like working these hard constraints into the loop is difficult. So I'm going to talk about 4 properties that I think matter a lot for applying foundation models to robotics that have sort of like enabled a lot of the new behaviors and abilities to come to fruition. First, I'll talk some about prompting and generally in context learning. Then I'll talk about how code generation can connect the behavior of a language model directly into movement of the robot. Talk about the general idea of pattern recognition, which I think is extremely important when applying foundation models to new regimes. And then finally about positive transfer, particularly when we fine tune these models or train with a lot of data as well as robotics data, what kind of new things we can get. So I think what we really want to, start with is some vision like this. Like you get a question like, I spilled the drink and I need help. How would you sort of break this down so that the robot can do it? The vision language model or language model needs to understand what the robot's capable of. It needs to know what the robot has seen before to be able to be trained on. It needs to know what's in the environment as well as the robot's state within it. And then finally, it needs to know what's actually like useful for this task. So on the left, we see a lot of things if you just like ask a language model how it might respond. And most of these things are maybe not that possible, like it using a vacuum cleaner or working with fluids or calling a cleaner. But things that it can do are like bring a sponge. And if it really understands its embodiment, it can sort of break that down into tasks that we care about. I'll start with some work, or first, yeah, let me focus on this, on the idea of in context learning, which I think is like one of the most important, I guess, breakthroughs of language models that has allowed them to be applied across the board in very general ways. So, I mean, I think hopefully this is not particularly new to anybody, but the idea is that if you show a couple of examples of how to respond to a question, the structure of the question, how to think through the question, the language model or vision language model or whatever foundation model can sort of understand that pattern and extrapolate from it. So given the exact same queries for like pairs, but with different answers, it realizes that this is about whether this is a positive or negative statement, and this is about what field the quote is in. So it can recognize that this last thing is about finance, and this is about this is a positive statement. We can use the same thing within robotics to make sure that the language model sort of understands what the robot's capable of, and we can even do this with vision language models. So the way we do this, and I'll start kind of like at this is maybe like a year and a half ago, and then go through sort of how we're thinking about some of these things now. But we can provide a bunch of examples of tasks that the robot can do and ways that it can respond. Like here are the objects that it can pick up. Here are some plans basically of how you should break this down. And now, given some new query, it can sort of extrapolate from that structure that was there. And instead of responding in all the possible ways that might be on the internet, it can respond in ways that are specifically possible for the robot. So we can look at the different responses of it. So if we said like, how do you put an apple on a table? And you've seen these other examples. So maybe some of the things that it can respond with are finding different objects, picking up objects, putting them down, going to different locations. And if you're kind of blindly looking at this as just a language model, you might say like picking up the apple makes the most sense. So another problem that we have is this grounding problem of like, you actually need to know what's in the world. A way that we can do this as sort of roboticists that we can bring to the table are ideas of value functions. At the end of the day, on the left side, we have a bunch of probabilities of what's useful. And on the right side, we have a bunch of probabilities of what's actually possible. So together between the two, we actually have this idea of what was useful and what was possible, and we can figure out which thing is sort of the like right middle ground between the two, and adjust to actually like finding the apple. That the fact that the robot is in sort of like no man's land means it needs to locate the apple before it can pick this up. And I'll talk through a couple like ideas that build off this concept, but essentially we need not only this like prompting for it to know what's possible, but we need some degree of grounding to embody the language model within the world. We can then plan, our task and continue planning forward as we execute with the robot in the loop. So yeah, like really driving this home, you have a language model that's giving you probabilities that things are useful, and a affordance model or value function that's giving you what's actually possible. We call this algorithm SayCan, and it basically executes that in the world and builds up a plan. But one issue that we have with this is that we basically like have enumerated a very specific set of skills that the robot can respond with. But if you went to a scene like this, we need more, I guess, general ways to provide this grounding. Now, if we look at like the regular decoding of a language model, it given the previous task or the previous text, it's going to fill in like the next token sampled from some like probability across all the possible tokens that we can respond. So it turns out we can basically guide this decoding. We can take the language model's response, but also some like value function from a policy, some like affordance, and directly at a token level guide the decoding, ground this decoding of the plan. So here the language model outputs some, here's a bunch of things you could do to pack a picnic box, and then the value function or the policy comes in and says, well, these are the things that are actually in the scene, and then reweights basically the probabilities, and then we can go and execute them. We can also do this with like a preference, like maybe human likes certain things, like they like Pepsi and not cake, or safety constraints can actually be worked in here. So this can be really nice because we have this general framework where we're just working across the probabilities of the decoding. And in action, it looks like this, and it avoids some of the things that maybe a robot shouldn't touch. This is like really easy to sort of like add in the constraints and even natural language. as well as like preferences of the person. We can work this within navigation, where the grounding or this decoding, this grounding function comes from what's actually within the scene. And then we can also like roll this out in a full environment, and say we have something like, I spilled something. Can you, I can't remember actually what this will be. I spilled a Coke on the table, and I want to throw it away and have something to help clean it up. I could maybe speed this up a little bit, but it's nice because we can actually look at the probabilities and see, the language model is recognizing the first thing it should do is find the object and then pick it up. The affordances are also saying which objects are available. And it's like very like straightforward to roll it out in the real world, and also general because we can just ask it through natural language. But essentially this goes on to continue to find the sponge and bring that. So it's thrown away a Coke can and then also brought something to help clean up. But there are also some limitations of language. Some of the things even that I had before can be relatively difficult to connect all the way down to actions for the robot. So like the topmost bowl, moving things into a line, weighting, things like this that actually have some sort of like conditional statement can be relatively difficult to then like connect these to actions. So I'll move on to the second property of foundation models that is really important, specifically applying to robotics. They're really good coders. Essentially, you take all of GitHub, you take all of these like large resources. There's a ton of data of code online, and also the quality of that data is extremely high because the code generally needs to actually run. Like there's some actual like check on top of this. We see that it scales very well with the number of parameters, with the size of the model. So clearly this is something that's somewhat emergent and well situated to improve as models continue to improve. And at the end of the day, code is sort of what a robot is running at the lowest level. It's connecting some like control APIs and perception APIs down into some logical reasoning and then executing that on the robot. So we should leverage this idea that language models can use code to command our robots. So we essentially prompt the language model to understand the perception APIs that are available to it, as well as any control APIs. So perception APIs might be detecting different objects. Control APIs are like a pick and place, but it can also do things like write if statements, write additional code like is something empty, and do somewhat of the logic there. It can leverage tools like NumPy and SciPy, and this is SciPy, and this is like what was actually running on the demo before. But essentially, it's like a really flexible and expressive framework to say things. And what's nice is, again, the data has come from sort of everywhere. So there's like robotics textbooks, and it can like directly write a controller for cart pull. It can do it in different ways, either based on prompting or just like what it generates. It can write a bunch of different ways to do this control. It can also understand like different languages. It can understand emojis. It can understand different embodiments based just purely on somewhat of the prompting. So essentially just tell it the actions that are available. In this case, move up, down, right, back versus turn left and move forward. So, and it can extrapolate that there's probably other things available to then take this task and turn it into actual code, which is like pretty much trivial now to execute onto the robot. And because it was so easy to execute on the robot, we actually put it on like a bunch of different robotic platforms. So we have like drawing, which I think one thing that was really cool is not only could you like draw this hexagon down here, but you could also then ask it to erase that hexagon, and it would remember, okay, here's where I went, and basically run this code in reverse to use the eraser. We can connect it down to navigation in a mobile manipulator. And then we can also do a bunch of tasks in this more like tabletop block domain that we were looking at earlier. Some of them might have if statements. Some of them are, waiting for something to happen or have a while loop in there. Code is just like so expressive that it's extremely nice for this. Not only can they write just like general code, but There's also some things that are better expressed through rewards. So if we try to just have a language model write the like code to have a dog stand up on 2 feet, so this like quadruped robot, it could like tell you the joint angles that it needs to hit, but without a controller, it's hard to really connect that all the way down to actions. But setting the like reward terms for this is actually pretty doable. And then we can just have some motion controller optimize over those reward terms using basically MPC. And you can directly apply this and do things like even long horizon things like this. The one on the left, I think, is app on the drawer. Yeah, is there a question? Or
No, there's no question.
cool. Or like something as crazy as like have the robot moonwalk. This is like, I mean, I don't even know how you would like try to code this, but some of the like the reward for it is actually not very difficult. It's like have the like the legs moving forward, but the whole body moving backwards. And we can even put this on into the real world to pick up different objects. You need some sort of like sim to real to describe the scene to then like optimize over with the MPC, but it's pretty straightforward to connect to the real world. And essentially, like this reward code is I think a very general concept. And when you can have a very like powerful optimizer over this, you can express pretty complicated motions. Even like here compared to human, I think it's like half the speed or so of a human because this like motion optimizer can be so quick and can be so expressive. Now, taking like a step back at, we've talked a lot about how prompting can guide your like the way that you use a foundation model within your robotics context. So I talked about SayCan, where maybe we prompt it to, given some task, output natural language actions. I skipped a few of these, but others that include code and just ways to sort of express. We're sort of like moving down and down this chain of in context learning, where we're like really leveraging the ability of the foundation model to see the structure that you've given it and the abilities, and then extrapolate from there. I think this underlies like a really important factor in context learning. We think a lot about how in context learning allows you to access the semantics, the semantic knowledge that's in a language model or a vision language model, that these are sort of like they've learned just this like vast repertoire of information from the internet that we can then go and sort of retrieve. But there's, I think, a second, I guess, factor within this that I think matters a lot, and that this is the idea of like pattern recognition. So at the end of the day, a lot of these are they're just tokens being mapped down, and in context learning is really about grokking the pattern that is being expressed through the prompt and then extrapolating from that. So one thing we try to do is just take like the most general patterns that we could, which came from like the abstract reasoning corpus, which is essentially like a written IQ test. It's recognize these patterns and then figure out what the next step is. This one's relatively simple, but if I've like gone through a lot of them, and some of them get very difficult. And what we really wanted to do is remove any sort of semantics from this and just have like the most abstract patterns possible to see to what degree can language models act as just general pattern recognition. And it actually works extremely well, or well to an extent. And I think as language models get better and better, this ability improves. So compared to a bunch of things that were built specifically for this task, including manually engineered things and learned approaches, a language model with just basically tokenizing the input extrapolates really well and outperforms, gets state of the art on all of these. So there's something in this, I guess, just like basic intelligence that comes with pattern recognition. And there's a lot of ways to apply this then to robotics. So we can show it a sequence and see that it extrapolates that effectively. So a sine, a sinusoid, or something actually on the robot where maybe you've shown it, here's the way to move, and it will just keep continuing to do that. And it seems to like work well for, we just like drew some random shapes, but you can also do some other interesting things. Like you can show a sequence that is improving. So if I showed it a bunch of like unlabeled examples and then just prepended each line with a reward. So what's like actually happening here is I'm showing it a bunch of states and then an action and then states, actions, and then the reward for a full trajectory. I don't actually tell a language model, this is what you're seeing. I just give it the numbers. And then for the next one, I prompt it with a higher reward. And it actually naturally generates higher reward trajectories. It figures out what the low level pattern is there and creates like an improved controller in this case. If we looked at this, it's pretty difficult to like understand the nuances of like why I'm doing one thing when and in another at another time. But what this actually is a rollout of cart pole, which is very straightforward. But when abstractly looked at these patterns, it seems kind of difficult. But the language model can sort of grok these. So we keep prompting it with higher and higher rewards. When it rolls something out that's a lower reward, we just put that into the replay buffer and we sort this buffer by by the reward of those. So it's trying to bias it towards moving towards higher and higher things. And we keep prompting it with saying, no, generate the highest reward, generate the highest reward. And it actually improves until the point that we get a like pretty high quality controller from a language model for this task. Now, I think these are really nice because they really pull apart the idea that there are these two properties between the semantic knowledge of a language model and the just general pattern recognition of a language model. That pattern recognition means that we can apply them in a whole bunch of tasks that like, or maybe non-linguistic, not the kind of thing that are represented on the internet, things that actually, are very akin to what we care about within robotics that maybe weren't otherwise there. And I'll kind of skip to the end because I think at the end we get like a pretty decent controller that can hold it up for a period of time. So I've talked so far a lot about in-context learning, whether through pattern recognition, getting it to code, or getting language models to plan these long horizon sequences. But I think we can get even more if we fine-tune these language models. It's generally known that you get this, I guess, positive transfer from the internet scale data to whatever your tasks are. So we want to see how much can we push that for different robotics tasks. So the first thing we did was this work called Autonomy, where we basically we started with a very large foundation model, a language model, and a vision model. And we also threw in a bunch of robotics tasks. So it had some experience from a lot of our different robots, as well as VQA tasks, vision tasks, language only tasks, and then applied it across a variety of different robotics regimes to see basically how well does this embodied experience benefit from positive transfer from the internet scale of data. Now, the way that it worked is we gave it a bunch of these tasks. So there's like mode manipulator tasks, general VQA tasks, language only and internet scale vision language model tasks, and then also some tabletop manipulation and task and motion planning problems. So always here, it was sort of like at the language level where, outputting plans for the robot to then execute. And the way that we do this is essentially given some pre-trained language model and then some embedder, we just project the embedder into the token space of the language model. We fine-tune that embedder and we fine-tune the language model to start to understand what those tokens potentially mean. So these may just be image tokens, but essentially we can just map them onto language tokens and have the language model understand this sort of like dual meaning of these tokens, that sometimes they're language tokens, sometimes they're vision tokens. And this is like a pretty expressive way, I think, to connect these two and really like piggyback on the initial knowledge that exists within the language model, as well as maybe the initial knowledge that exists in, say, like a large vision model like VIT or whatever other like embedder you have. And so given the like text tokens, embedded tokens, you just put those all in and then generate language tokens to answer whatever VQA task might be, or the mode manipulation or task and motion planning task. So what's really exciting here is that we do see this positive transfer. So given the exact same model, trained only on task and motion plane data, only on language table data, which is a 2D board setup where we're pushing blocks around, and only on the SayCan data that I showed before, which is a mobile manipulator driving around. Each model does okay. It's 50%, 25%, and 50%. But if we put all of those in there, as well as the internet scale of data, they all kind of help each other. They lift each other up. We really see this positive transfer. We see how scale matters, how the internet can sort of propagate down to stabilize learning of policies for these other ones. We also see that as we get larger and larger tasks, we actually see a lot less forgetting from the language model. So at sort of small, is to 10 billion parameter models, the language tasks get basically destroyed when we add in a bunch of vision stuff. But when you get to a really large model, it actually has enough room to sort of understand each of these and make better connections. I'll talk a little more about how scale is important in some of the coming slides. We can get some things for free, like we get a multimodal chain of thought that just kind of falls out of this. Chain of thought comes from just the language model's understanding of the world. And once we kind of train it to understand the image embeddings, it can extrapolate from that. So asking things like, are there more dogs or cats here? And it counts them and it reasons through, okay, there's 2 dogs, 2 cats, so there's an equal number. Some of them are pretty complicated. I probably wouldn't have been able to get this. Who are the teams playing this photo? What year did they last win the championship? And who was their star player? And you start to see not only the way that it reasons through, so it figures out this is the person we're talking about is Chris Paul, but you also see some of the remnants of the language model that it says, I'm not sure if this is correct. I'm not a basketball fan. I just Google it. You really see that it's kept a lot of the language understanding there while also still being able to process the image and apply it. I think this one's also very interesting to me because it's, you're a bicycle. Can you go down this street? It's kind of complicated. There's do not enter, except, but then in visual you see the bike. So you have to understand that that's actually a picture of a bike. Connect that into words, and then realize, okay, yeah, you can actually go down this. Other things like what's different between these two scenes, and this is actually Pete, a researcher from our team, took these pictures. So they definitely weren't on the internet. They weren't trained within it, and it can recognize what the difference between these two are. That one has the sunglasses in it, as well as do some sort of more complicated processing. We can apply this down to robotics tasks as well, and command the robot around. And maybe here's some echo again. If one person can mute or so we can have it understand not only the scene but command the robot to go and execute something even under adversarial disturbances, and replan essentially. We can have it also execute on 2 different robots because it's such a general model that it can understand basically the scene of each. Now, here I've talked a lot about how we can use language, train in language tasks and have it command a robot, but we haven't really focused all the way at the lowest level of the stack of actually connecting this to actions. So now I'll talk about how we can fine tune and actually get actions out of these. So we had some previous work called RT1 where we took 100,000 demonstrations, trained a robot specific architecture to be very efficient, to understand images and a language instruction and output actions that move a robot arm as well as move a robot base. And it worked pretty well. We got very high success rates, but we got somewhat limited generalization from this. So the idea here was, can we just instead remove the specific architecture and replace it with a VLM? Just kind of drop in the VLM. So RT1 started with discretized actions where we broke the actions down into buckets that move the arm. Vision language models also have these discretized tokens. So we just kind of need to map the actions down to tokens and then add this to the training mixture of VLM and see if we kind of get the generalization and the positive transfer we hope for. So the way we do this is very simple. I mean, we just literally map the actions, which were, moving the arm and the gripper. They were like some numbers that were discretized into bins. These are numbers like, 1, 127, 115. So we can map these actually directly down into text and just train the VLM to, when seeing a question like, given this task, what kind of action output, it can just output this string. It can also answer VQA tasks and do general language model tasks, but it can also output actions. We see some sort of like positive transfer here. We can also do things like floats or extra IDs, which are the tokens at the end of a language model that haven't necessarily been trained on. But we found that integers work extremely well because they map to a single token, and there's actually a lot of data and semantics already imbued within the language model for these. So what this does when we throw this on there is we get our first vision, language, and action model. So it's these, we have trying a couple different ones, a 5 billion parameter model, a 55 billion parameter model. Again, on all these tasks, we have like um, different languages, different VQA tasks, and then also these robotics tasks. So like, what should the robot do to execute a specific thing? So maybe it's like pick up this chip bag, and then we fine-tune on all this. Specifically, we keep all this data around. There's like the huge web scale pre-training, and then our like 100,000 robot examples that were collected across a bunch of different robots in a lot of time. To do this, we use the same process we described before, where we basically just train an embedder to take the tokenization of the image of the task and then output the tokenized actions as though they are just text. And then we just run this at a robot speed, so maybe 3 hertz, and then we basically see that we can actually try new tasks that we haven't seen before. So a lot of, we just kind of like played around to see what sort of like emergent skills. And it's interesting because normally which skills your robot's going to be able to accomplish. You sort of start out with, well, we trained this data, and then within these regimes, it's going to be able to extrapolate. But here, because we're sort of connecting the internet scale knowledge, the foundational knowledge from the vision language model to actions, you don't necessarily know where it's going to transfer. And it turns out it does a really good job of somewhat transferring like object knowledge. So it knows who Taylor Swift is. It knows that which animal is a different color than the other ones, that a horse is a land animal. It knows different flags, like very kind of like abstract things. It seems to make the connection across. And we see compared to a baseline and then RT1, which is only trained on the robotics data, and then 2 different VLM models. Both the VLM models vastly outperform in sort of emergent skills and do equally well on the sort of in-distribution tasks. So some of the skills that are saying, you can see here, one like in the middle, I think is like put the strawberry where it belongs. So it has to understand that it goes with the other strawberries. Move the banana to the German flag, or I think in the top left one actually has some like math in it. It's like this: move the banana to 2 + 1. So it's like really connecting this language reasoning directly down to actions. We also did a lot of like qualitative evals across some of the same, I guess, diversity that we had tried previously for our work, Robot Transformer 1. So these were things like first just in distribution, where it performs about the same, but also new objects, varied backgrounds, new environments. In general, like across the board, both different vision language models, one was PaLMi and one was Poly, perform extremely well compared to the baselines. We also have a couple, like, I guess, takeaways. One is that we tried both training these models from scratch. So just seeing like, what about does pure size and pure architecture matter? And we see in general, these are these like red lines, they don't work nearly as well. Then we tried fine tuning, where you start with a vision language model and then you train it on only robotics data. And that works decently at certain things, but that's in green. But generally, we almost always see a benefit when we co-fine tune, which means we keep the vision language internet scale data around and train at about a 50-50 ratio of robotics data and internet scale data. Another thing we see, like the wide lines are always the 55 billion parameter model and the narrow ones are 5 billion, we see that size actually matters a lot to get the generalization that we care about. And then lastly, we tried it on 2 different VLMs, and both worked very well. So it seems like a general lesson across, I guess, internet scale, large foundation model training. We can also do things like chain of thought with this to connect it to new tasks. I really like the one at the end here where it's I need to hammer a nail what objects would be useful, and it has to connect it down to the word rock, for example. So this is like definitely out of distribution, but the language model can the vision language model can jump in and say, okay, I see a rock. Now that I've like grounded this into the action, it actually goes and performs it. Some things that we didn't get that maybe we expected or hoped to get would be maybe no new motions or tasks. And I think some of this has to do with the fact that we have a large diversity of objects in our training data set, but not that many motions. So there's still some work to be done to, I guess, get enough diversity in motions and things like that to have more generalization emerge. So I guess speaking of this diversity, a lesson that we learned in RT1 and this work, Robot Transformer 2, was that data size matters a certain amount, but not nearly as much as data diversity. So the success rate goes down much, much quicker if you have, if basically we removed just like a random number of or a random number of data points, and on the purple line we removed the data points that had the least, or the tasks that had the least amount of data. So basically we're controlling for data set size versus diversity, and we really see that diversity is the most important thing. So what we try to do is let's scale up the data and make it as diverse as possible. And we recently, if you look at what's happened on all the other large data sets, usually people go and find them on the internet. They're naturally out there, but robotics doesn't really have this. There's not some large scale model that exists that we can just go and grab. So we went and collaborating with, I think it'll say in the next slide, but it's some 60 maybe institutions. We basically created a huge data set with different robotic embodiments, with many different scenes, with a lot of different skills, and then with different objects that we're working with. And yeah, I guess the numbers are here. There's like 60 different data sets across 34 different research labs and 22 robotic embodiments, as well as over 500 skills that are represented from them. And these are things as diverse from like cable routing to stacking to pouring. You can see some of the data sets like in the background, but essentially, we tried to scour and far and wide, and I think we want to also continue to grow this data set. So we have a kind of a call for further data and research. If people are interested, you're welcome to get in touch. Then we tried it on our 2 robotic policies, RT2 and RT1, which we call RT1 and RT2X. Again, we just discretize the action spaces of all these different ones. We actually didn't have to do very much. We basically just like normalized the action spaces, discretize them, and then threw it on the robots. I think one might have expected that there'd have to be a degree of cleverness to get this to work well, and it turns out it just pretty much works. So you can see actually on the right, like each one has a different action space, a different frequency even. Some are in velocities, some are in position deltas, some are in absolute positions. And it turns out if you just kind of like normalize each robots for its range, it basically works. And if some like don't have rotation, you just like give it a marker token of like the center token and don't output that. And now we tried comparing against a bunch of different models that were specifically designed by research labs. So they were previous works that had a architecture very fit to that robot, to that embodiment, that were published, that were really like very impressive works and state of the art. And in the vast majority of them, training on everything with just this like general model of RT1 actually outperformed the other baseline. And where it beat everything like across the board was if we just trained on only RT1 with just that data and not the rest of this open cross embodiment data set. So we see essentially a 50% improvement overall when we train on the huge amount of data. And all of this is open source and can be used to hopefully like improve results across the field. One thing that we did see though was when we had huge data sets, so like the Google data set that we had collected, some of like the bridge data set from Stanford and Berkeley, we didn't necessarily see the gains that we would hope with RT1. And essentially what happens is when you train on everything, we end up underfitting. So we then trained in RT2, so a very large model, and we see that it actually like learns from that and recovers the performance that we expect. But what's maybe most exciting is the generalization. So these are generalizations across the axes I talked about before, where there's like unseen objects, backgrounds, environments, and we basically keep the same. But this is expected because RT2 was like very good at this type of generalization. The VLM internet scale is what's providing the background knowledge, not necessarily these other robotics data sets. But on emergent skills, where we try things that a specific robot hasn't seen before, so a lot of these are executed on a Google robot that like only exists there, and there's like it either hasn't seen objects or it hasn't seen certain motions, but these motions are available in other data sets. We actually see a massive increase in the emergent skills that are available to it. So like a 3x, we kind of went around and tried to sample different skills that were available in other data sets and try them. And essentially, it seems like this positive transfer really, really happens. So that's sort of the end. I'll just kind of sum up, and then I can take questions. But so there are a lot of issues with using foundation models for robotics. I kind of talked about them before, but they're really general and interpretable, and certain properties mean that we can leverage them very effectively for specific domains within robotics. In context learning is a very powerful idea that means that you can just apply it to a new problem with very little effort. They have a lot of semantic information that's really useful to the world, but they also have a lot of pattern recognition information, which means we can apply it to arbitrary patterns that maybe one wouldn't expect. This is where you can now apply it to actions, you can apply it to self-improvement. We think that this means that you can apply it in a very general way. Their coding ability allows you to directly apply it to what already exists in a lot of robotics stacks. And then finally, fine-tuning has significant positive transfer, generalization to and robustness to backgrounds, as well as generalization to new tasks. So the bottleneck we still think is the size of the data sets that are available within robotics, the quality of the data sets, where foundation models are expanding, and we really want to kind of ride the wave of increasing foundation models, but we think we have some of the signs, especially this like positive transfer towards building a embodied foundation model. So that's the end of my slide. This is work by a lot of other people, many of which like aren't even pictured here over the last couple of years. But yeah, thank you. I'm open to questions.
Thank you very much, Brian, for the great talk. Let's open the stage for questions. So you can either type in the chat and I will write for you and I will read for you, or you can raise your hand and directly ask to Brian.
Great. Yeah, I closed the presentation so I can see the chat now too.
Yes. So maybe I'll start with the high-level icebreaker. Hopefully, people will prepare some questions later. But it's so this relates also to some work you did in the past. I was following your PhD work actually, and here today you presented some results in which you apply these foundation models to the entire stack. But what are your thoughts on applying it just to part of the stack? For instance, let's say motion planning or controls.
Yeah, I mean, I think in certain regimes where we have, I guess, like very strong algorithms, then I think in a lot of cases it makes sense to just apply it to part of the stack. Some of the like works that I didn't include here were around navigation, for example, where maintaining a map or like topological map of the environment and using things like SLAM actually work quite well. In those cases, the semantics can help you kind of explore the world, and so you can bring these in as sort of like a heuristic within graph search or the like. So I think in cases where the like classical algorithms work well, in cases where like memory is important, explicit structure and safety, then I think it makes a lot of sense to just work them into the backbone that exists. I think that still for like motion planning, for instance, I would probably still use, you know, like RRTs and PRMs and things rather than just trying to like blanket use an LM.
Okay, thank you. Any other question from Brian? Okay, so there is a question in the chat. How robotics will be next frontier? Why are you not considering healthcare and LLMs or
I think
robotics?
A lot of our research, we sort of used what was available to us. So, and we work in an office. We have like office kitchens, and so we did a lot of things in an office kitchen, and we're just sort of motivated by those ideas. I think in a lot of cases, you just do what's convenient, the data that we have available, the environments that we have available. I think there's probably going to be a lot of benefits similarly to healthcare down the line. It just isn't something that's available to us. I think there's also maybe some challenges around safety and general like hard constraints that exist within the healthcare field. And then how does it do for long horizon task planning? Other limitations of these models that could be pushed further. So I think in general, I would say directly using a language model for long horizon task planning. I think there's a lot of works that are around the idea that, you know, with titles like language models can't plan and critical and, you know, basically critical of language models planning. And I think that a lot of them are correct that right now this is a limitation of language models. But what you can do is work these language models into existing planning regimes or use some sort of like forward planning within a language model. And I think those types of approaches are extremely effective. But I think they are, at least right now, an inherent limitation of these models that they aren't like, they don't have this world model doing forward search.
Then there is Rice University someone from Rice University saying it is very interesting to see how novel robot behaviors can emerge, but definitely maybe in some situations you don't want that. Have you explored the ways to avoid these situations?
Yeah, I think one thing that's really nice about language models is they're so interpretable, like in natural language, that it can actually be a lot easier, you know, algorithmically sometimes writing down constraints such as like what things are unsafe, knowing that like maybe the robot shouldn't pick up a knife or a weapon or a glass with water in it. Can be really hard to write down in hard constraints, but really easy to write down in language. Really easy for a foundation model that has actually some like more general understanding to understand. And so in a lot of cases, you know, I talked about it briefly with this grounded decoding work, but you can actually explain the rules of the world and the foundation model understands that these are like not the things to do. So I'm actually like excited in a lot of ways that safety becomes so much more interpretable with these models.
Yes. So there is also people asking whether these tools, some of these tools at least, are open source, specifically Palm-E and POLI.
And Poly, I guess, is the other one. Right now, none of them are open source. I know there's like many new vision language models that are coming out that are open source. Obviously, like OpenAI ones, but also like ones that are completely open source that probably have a similar performance to some of these. But otherwise, but yeah, the ones that I mentioned specifically, unfortunately, are not.
Okay. So there is also another question about, I think this is nice, especially because you were showing demos and stuff. So people asking, you're utilizing very big models with many parameters. Does this mean that we should forget real-time applications on the edge?
So I think I guess there's maybe like two answers to this. One is that even though they're large, a lot of them are actually pretty fast, and there's significant research and interest in general in the like the broader community and speeding these models up. Even like running the 5 billion parameter poly model, I think the actual run of the model is like 50 milliseconds. So you could run that at you know at 20 hertz. 5 billion parameters can fit on a GPU that's local. And so you could actually run that like extremely quickly. You have some latency going to the cloud. I think we could have actually run it at maybe like 10 hertz. So it's not bad. But for applications where you really need fast performance, say maybe quadrupeds where the low level policy is running at 50, 500 hertz, I think something where you potentially have two systems, like a high level system that's doing some decision making at a slower rate, and then a local sort of like edge system running seems like a good way forward to sort of break that. I don't think though in any way that this like precludes real-time edge applications.
Okay, cool. Then there is Alessandro, who has an eye for the detail, is asking, why is it the case that sometimes fewer parameters outperform bigger models? This is visible in some of the plots or the graphs you actually show.
Yeah, I don't think I have like a particularly satisfying like way to describe this or way to like, I guess, yeah, like on unseen backgrounds, for example. I know this one we see it. I'm struggling to remember explicitly other ones where we see that happen, but I think some of it is maybe within the noise. Some of it may be you know, a characteristic of a specific thing, like just like the amount of data or the amount that the like robotics data takes up of the overall like latent space of the model. But I don't have any like great reasons why. I think it's almost like noise. Like you sample enough different tasks, you'll find a few things that for some reason the smaller model performs better.
Mm-hmm. Then there is a question from Tom, who says, first, how do you reject bad code generations? And then second, what about code or language generation in an emergent grammar for a particular scene?
So for the first one, I mean, I think you have like some signs when you run code, whether it succeeds or fails. If it fails, you could feed that feedback directly into the language model and run it again. In general, though, we find that they're pretty robust at least creating like runnable code. If it makes mistakes, we don't have any like great solutions here. You could do something like connect a VLM that provides feedback, or in some way provide feedback to the language model, and it can understand this like kind of nuanced feedback. But yeah, I think like providing feedback mechanisms is generally the way to do it, but providing a general feedback mechanism is still somewhat limited, and maybe like a VLM can help. And then
yeah, there is a specification for the second part of the question. For instance, in 2, I observed the can of SayCan.
Yeah, actually, so for the implementation of SayCan, we actually constrain the way that the models can respond. We use what's called a scoring mode, where we say, you know, here are the ways that you might respond, and just score each of the probabilities of them. That's like one way we can constrain this. I would say in general, that was important a year and a half ago with the models that we had then. With the current models, it's relatively rare that it outputs something that isn't feasible or like possible for the robot. So these needs to constrain or restrict it become less important. Except I think your follow-on point of like the grounding, I think still is like required, and yeah, it can be sort of mapped to are we just constraining it to only respond in things that are possible is a reasonable way to think of what the value function is doing.
Mm-hmm. Will foundation another question, yeah, other more degrees of freedom, for instance.
Yeah, I think definitely. I think I mean, here we have you say 12, but we have 7 in this. It's like not a big difference. Obviously, like language can output very high dimensionality ones. Others are using language models as image generation. So there, the like output space is 64, 256 tokens, and it's able to learn over those things. So I don't see any reason why it wouldn't be able to generalize to those. Generally, we worked on these because this is the data that we had, and this is like the manipulation problem we felt was the most constrained by current methods, rather than a need for limited degrees of freedom.
Right. Is there any other question for Brian? Since there was a lot of interesting discussions going on, but doesn't seem so. I guess you left your email in case people want to reach out with other questions, right?
Yep. Yeah. Let me move it back.
Oh, okay, perfect. Yeah.
And thank you everybody for all the questions. Really.
No, thank you. It was very interesting, and I look forward to seeing the next steps. What you produce.
Thanks.
All right. Take care and enjoy your day. Bye bye.